Okay, now we're going to look at the answer of the questions I asked. For the first one, what I asked is, if we just dissolve all of this thing into water, what kind of particles can be formed in the water solution? So if you look at the solubility, one thing that you have to consider is about the intermolecular interaction. If they can interact with water, it can dissolve into water. But now the molecules have quite a complicated structure. And for example, in D, right, we have from the right hand side pink color, this cannot be dissolved into water because you have such a long chain nonpolar compound here on the right. But if you look at the left hand, you have charge, right? You have sodium ion, phosphate ion, things like that. And you also have many oxygen on the left hand, which can have a kind of interaction with the water by hydrogen bonding and everything. So you have to weigh between, I would say the intermolecular interaction of the molecules is quite complicated, and it can be divided into two sections. The left hand section is the polar part, right? So it can interact with water very well. But on the right hand here is non-polar, it interact with them among themselves, right? So I will just go through from the first one, A. We call A as fatty acid, and we put it into the lipids because it cannot be dissolved into water. The reason behind this is because of the London force on the right hand. They pack themselves together by the London force. And the carboxylic acid group, even though we have potential for interact with water by hydrogen bonding and many things, but we know that fatty acids cannot be dissolved into water. This is quite a common knowledge from your high school. So this one cannot be dissolved into water. Hydrogen bonding here can interact with water, and also they can interact with themselves as well. So instead of having hydrogen bonding with the water, it can hydrogen bonding with the next molecules or other molecules nearby, things like that. So for A, it's insoluble. So A is here, insoluble. So if we want, and if you look at the B is also insoluble because the structure is similar to A, right? The right hand part is still nonpolar. Even though you have saturated or unsaturated, they are nonpolar, they have only London force. So it's very hard to dissolve this part on the right hand with the water. So A and B is insoluble, obviously. So if we think about A, as you can see, we have London force on the right hand, very long, and then on the left hand, you can have hydrogen bonding. So normally they just pack themselves up together as a solid. So if we want the A to be soluble into water, the thing that we can do, there's two possible alternatives. The first thing is reduce the London force on the right hand, or another way is increase the interaction of the polar part on the left hand, right? Because we have two parts, no? Non-polar and polar. Non-polar cannot be dissolved into water. Polar part dissolve well into water. So if you want this fatty acid to be easily dissolved into water, you have to cut down the non-polar part or facilitate the polar part, right, to have interaction with the water. But for non-polar part, this is carbon-carbon bond, single bond, which is very strong. You cannot just cut them down. What you can easily kind of modify the structure of A is to increase the polarity of the A. And to increase the polarity of the A, it is very straightforward, because from A, right, A is the acid. So you just put sodium hydroxide, then you can change the A to B. From A to C. Now, by adding sodium hydroxide into A, then the reaction takes place, right? It's acid-base reaction. Hydroxy group here can then take away hydrogen atom, right? Deprotonation, so you have water out. And sodium ion, carboxylate ion attached, so we have sodium carboxylate. Sodium carboxylate is very, very polar. You have charged in the particle. Because you have charges in the particle, positive and negative, when you put into water, this is sodium salt. And sodium salt almost always dissolve well into water. So after you put it into the water, sodium was like dissociated into water by hydrogen bonding, by ion dipole interaction to be exact. And then for C here, because for A, right, for A, you have like this one, and this can have hydrogen bonding. So you have like many of the A molecules, London phos packed together, hydrogen bond packed together. So what you can have is kind of solid, because they just pack themselves up together like that. But now, instead of carboxylic, you make it to be carboxylate. If you make it to be carboxylate, so that means you have a long chain nonpolar. And this one is carboxylate, which is anion, negative charge, right? Sodium ion is dissolved into water, right? Disappeared already. So if you have two A molecules, so London phos and London phos can packed up together by intermolecular interaction of London phos, right? But the polar part now is negative charge. So if you have many A's comes together, so you have London phos are trying to go together, right? Because of the London phos, no? So long chain hydrocarbon trying to be together like that, because they have to leave the aqueous environment, because they have no interaction with the aqueous environment, so they pack themselves up together. But for the polar part, which is now turned to be negative charge, and yeah, sure. So negative and negative, you have electrostatic repulsion, right? Because of the repulsive force among negative charge, so they trying to stay away from each other. So what you can have is like this, right? Because negative charge trying to stay away from each other, but for the long chain hydrocarbon here, trying to stay together, because they have no interaction with the water, so they interact among themselves and then pack up to be like this. So if you turn A to be C, or even B, dissociate with sodium hydroxide, then you can have the micelle structure as well. So that means the salt or fatty acid can pack themselves up into micelle structure. So C would be here, but it depends actually. So if you have very diluted concentration of C, then it would be 1, right? Because it can dissolve into water. Because if you have very low amount of the molecules in the water, very low concentration of the molecules in the water, so it's the possibility that the tails part can pack up together is rare, right? Because you have less population, right? So if the concentration is very low, it would be resulted in like one. It's like monomeric compound dissolved in water, random floating around in the water freely, just like that. But if you have enough of the concentration, then you can form the micelles. But anyway, if you have too much of C in the in the solution, they can just precipitate it out as well. C is actually your soap. Normal soap, SOAP soap, right? Normal soap is C. So you can see that if you have like a bucket of water and then maybe a bar of soap, right? You put the bar of soap in and then take out quickly. So you can see that in the water, there's almost nothing that you can notice in the water. This is because you put the small amount of the molecules into water, so they completely dissolve well in the water. But if you put the whole bar of soap into the water, they cannot dissolve, right? And you can see the bar of soap sank down into the bucket of water, so it's like insoluble if you have too much of the molecules. But if you have a bar of soap again, and you may just stir it in the water for maybe some second, what you can see is the clear water tends to be a bit turbid, right? This is because the micelles is formed down there in the water. Okay, so C is like this. But now, if you look at D, E, and F, the thing is quite similar to C, right? May I just erase all of this kind of thing? So C is the micelles, right? But now, if you put like D, E, and F into the water, the differences between C and D, for example, C, you have negative charge with a tail of hydrocarbon. So negative charge trying to stay away from each other, tails trying to go pack themselves together, right? Because of the London force of the tails and electrostatic repulsion of the head, you have this kind of thing, you have micelles. But now for D, E, and F, instead of having negative charge with a tail, you have two tails. Right? You have two tails of the hydrocarbon chain. So instead of one tail, you have two tails. So if you have two tails, it is quite steric, it's quite bulky. So what you can see that you cannot pack it in cyclic style because you have just like two of the tails, right? Its bulkiness prevent themselves to curve up like that. So what you can do is just packing it into layer like this, into layers. So after you have a layer of molecules assembled together like that, so now think about the water environment. Right? The water can interact with only the polar parts. Right? With only the polar part. This is non-polar part, so water cannot come in and have intermolecular interaction. But the stronger intermolecular interactions is the London force. So instead of being like this, they can pack up and use the London force between tails to couple themselves up into bilayer. So we call this as lipid bilayer, right? Because it's the lipid, no? And you have two layers packed together, so we call it lipid bilayer. In your high school, you may have heard about it. A lipid bilayer is the structure of cell membranes, right? Cell membranes composed of lipid bilayers, and the lipid bilayers can be here. Okay, I will talk about it later. So from the lipid bilayers, if you have kind of, it's like a kind of sheet of paper. Oops, sorry. It's like you have paper sheet like that, right? It's have thickness, okay, a bit by packing up of the molecules. But if you have kind of these bilayers huge enough, you can curve them up and yeah, fold them into any kind of structure, in tubes, in bowls, and everything. So one possibility is fold this thing up into a bowl, and this bowl is called vesicle. Okay. So vesicle and micelles, basically, it is they have the same interaction, right? Non-polar part of the molecules have like lipophobic interaction. They're trying to catch themselves up together, pack themselves up together, like this and like this. So it depends on the bulkiness of the tails. If you have just only one tails, you can just curve them up into a spherical balls, tiny spherical balls. But if you have kind of two tails, so because of the bulkiness, preventing them from curve up, so they have to pack into lipid bilayer. And from a huge lipid bilayer, they just curve and then fold themselves up to be a balls like this. So this is the vesicle. So vesicle and the whole cells is kind of the same thing. Basically, the vesicle is the structure of D, E, and F in water in aqueous solution. Okay, so because of two tails, right, the packing style would be dropped into something like that. I know. So as you can see, everything happens because of the intermolecular interaction, London force, and hydrogen bonding. What else that I want to discuss about is D and E, which is very similar. Actually, D, E, and F are about the same thing, right? But E, I introduced the cis isomer and saturation into the structure. So can you now answer what would different for the lipid bilayers that was formed by pure D molecules and that was formed by the E molecules? Okay. I give you maybe several minutes, think about it. So you can pause the video right now, and then after you finish, I will just show you the answer, what is the reason behind and why this cis isomer is very important in the cell membrane. Okay, so pause the video now. Okay, so if you finish thinking about it, now let's see the what really happened here. So at the very beginning of the sections, I've already talked about the cis isomer and saturated. That firstly, the melting point of fatty acids, of saturated fatty acid, is higher than the melting point of the unsaturated fatty acid. This is because of the packing style of the long chain hydrocarbon there, right? So if you have a kind of long chain here, the packing is very nice, right? The long chain hydrocarbon elongate to the right hand side. So you have London force on the right, you have hydrogen bonding on the left, things like that. But now, if the long chain part is cis isomer, like this, so it's a lot more complicated because the packing system is ruined by this kind of double bond, right? So again, the bilayer that was packed by fatty acid, saturated fatty acid, it is packed up nicely because the hydrocarbon is quite flexible, no? So it's packed quite organized, well organized packing like this. But if one of the cell membrane is packed in this style, so you have cis isomer. So after you have cis isomer here and cis isomer here, right? So it's like that. So it ruins the packing system of this one. So the density, or I would say the fluidity or density, is quite the same thing. So the packing with unsaturated will ruin the well-organized structure of the unsaturated of the nonpolar part in the middle. So it's loosely packed, I would say. But if you have only the saturated chain, then it's densely packed, right? So with unsaturation here, it's loosely packed. With saturation, it's densely packed, and it's very important for the next question. Okay. Now, if you know the principle of this, you can be sure you will have the right answer for this question. So, if you want to change the answer from your homework, do it now. Pause the video right here, or I will go to give you the answer of this one. Okay? If you want to pause it now. But if you don't want, I will show you the answer here. So the vesicle can be cells, can be many kind of things in the cells, because actually in the cells, right, it's like this. You have cells, you have nucleus, right? You have like Golgi apparatus, Golgi body, and you also have kind of vesicle around, right? When you have like something that the cells wanting to take into the cells, right? one of the way they can do is to make kind of endocytosis, right? The endocytosis mechanisms is like the cell membrane is curved inside, right? So your things, right, is then dropped into the sac, and from this, it go down as a vesicle. So this is called endocytosis. So the vesicle here inside, sometimes we call it vacuole, thing like that, no? Is the same, exactly the same thing as the cell membrane. And also, the Golgi body here, from your high school, you may have heard about this name. The Golgi body is exactly the same thing, right? So everything in the cells that, normally the vesicle is produced in order to transport things that is water soluble into the blood system or into or inside the cells, right? If you want to transport something, instead of let it free flow in the bloodstream, the cells or your body trying to make a vesicle over here and pack the water soluble thing inside. Because inside, as you can see, both sides of the lipid bilayer is polar, right? Outside is polar, internal is polar, external is polar. So inside is full of water as well. So water soluble molecules can be packed here. So the vesicle, sometimes you have kind of receptor on top of the vesicle, so the cells can send the vesicle into a specific area, thing like that. So it's a kind of transporter, I would say. Now, the transporter, the cell membrane, the Golgi body, or there are many types of cells and many types of kind of organelles here. So sometimes vesicles have to be very rigid. Sometimes your vesicle have to be very flexible, right? So in this kind of case, I give you the nerve cells. And as I said, this area of the cells is quite rigid comparing with the flexible tail over here. So that means the lipid bilayers that packed into these kind of structure have some part rigid, but some part flexible, right? So it's like this picture. If you incorporate the cis isomer into the structure, then the packing is loosely packed because of the steric effect from the double bond over here, right? So it prevents them from packing densely. That means the lipid bilayers that composed of unsaturated fatty acid is quite flexible because it's loosely packed. But if everything over here is saturated, so it can pack up densely. So if it packed up densely, it cannot move very freely. So it's quite rigid comparing with the cell membrane with the double bond inside. So as a result, the rigid core may compose of the lipid bilayers with very saturated things. So the rigid core shall be the packing from D or F. Okay, both D and F are saturated, so they can pack up into a rigid lipid bilayer. But if you have like rich of E, right, because of the cis isomer here, prevent themselves from densely packed up together into a very solid thing, solidity. So the flexible tail would compose of mainly E. I would say normally we can find all of this thing in the cell membranes, but the ratio of the things are different from area to area. In the core structure or in the membrane that needs the rigidity or need the rigidity of the membrane, the ratio of saturated is higher. But in the area of the membranes that have to be very flexible like this, or in Golgi body, as you may know from your high school, that the Golgi body is quite a flexible area in the cells, using for pack the proteins inside and send the protein out, things like that. So change from time to time. The structure of the Golgi body has changed from time to time. So to let it move freely like that, the membranes of the Golgi body or the membrane of the flexible tails like it have to be very fluid, right? Flows very easy. So it have to loosely packed from the unsaturated hydrocarbon chain like that. So it have to be E predominated. The ratio of E is higher in the flexible membrane, and the ratio of saturated is higher in the rigid membranes. So the unsaturation can then fine-tuning the properties or the rigidity of the membranes as well. Okay, so as you can see that the London force in your high school, you may feel that the London force is not important at all because it's quite weak comparing with other intermolecular interactions. But now you can see that the London force plays very important roles, the key roles actually, for the properties, the rigidity of the membranes and everything. Okay, no? So I think it's enough for the lipids, and it is enough for the topic of biomolecules. Okay, so I would end the biomolecules over here. Thank you very much for your attention. Thank you very much indeed.